Liquid Cooling of an AI GPU by Luis Vasquez, Connor Hayes, Luke Sodolak, and Owen Sheldon. The problem that we've been tasked with is that with the recent explosion of AI and AI integrated systems, the demand for computing power is increasing exponentially. This surge in computing demand translates to more power being drawn, which inevitably leads to increased heat generation. Overheating poses significant risk to electronics and performance, underscoring the importance of effective thermal management strategies like the one that will be discussed throughout this presentation. Some of the design criteria. We were tasked with designing a liquid-cooled system for GPU cooling and AI systems. This involves designing a liquid-cooled system specifically tailored to cool a GPU with a particular emphasis on use in AI systems. This design must incorporate a heat sink to absorb heat from the GPU chip and a circulation loop to dissipate this heat effectively. GPUs and AI applications are used, and this will be used in those to ensure optimal performance as well as longevity. Step one for our process was the heat removal method determination. In this initial step, we must determine the method of removing heat from the chip. And after careful consideration and discussion, we opted for the traditional approach by utilizing a copper block with fins encased in a leak-resistant housing. This method provides a reliable and proven means of efficiently transferring heat away from the GPU chip, setting a solid foundation for the liquid-cooled system design. On to step two, material selection. In the second step of our design process, we focused on selecting the materials for our heatsink. And after careful consideration, we opted to design the heatsink from copper due to its cost effectiveness, particularly for large-scale AI data centers, as well as the ease of machinability compared to other options. And while other materials may differ and offer higher thermal conductivity, facilitating more efficient heat transfer to the fluid, they're either prohibitively expensive or they present machining challenges, making copper the preferred choice for our liquid-cooled system design. Now for the components of our design. In this third step of our design process, we focused primarily on selecting the components for our liquid-cooled system. For the pump, we chose the EK Top Revo Dual D5 PWM, which is known for its reliability and performance in maintaining fluid circulation. To complement this pump, we selected the Radipac industrial fans for efficient heat dissipation as well as airflow management. And lastly, we opted for the Polymatech PK3 Nano Aluminum Thermal Paste. This ensures optimal heat conductivity between the heatsink and GPU chip, which promotes efficient heat transfer. Some more of the components. Continuing with our component selection process, we consider additional essential components for our liquid-cooled system. The radiator serves as a crucial element for heat dissipation, transferring thermal energy from the fluid, water, steam, whatever fluid we use, to the surrounding air. We've selected a radiator that offers optimal performance and compatibility within our system requirements. Additionally, we rely on a standard motherboard as the foundation of our system, providing essential connections and support for various components, ensuring seamless integration and functionality with the overall system architecture. This is just a diagram of our slide. Presented here, the top view of our heatsink design, featuring the chip with the fins. The chip's depicted as a square measuring 28.53 millimeters by 28.53 millimeters. This is the area required cooling within our liquid-cooled system. Additionally, the fins are illustrated with a spacing of 0.5 millimeters between each fin, featuring square shapes measuring 1 millimeter both in length and width. These fins are strategically positioned to maximize surface area contact with the cooling fluid, enhancing thermal efficiency. Now for the development of our thermal cooling system, we have our thermal circuit. This thermal circuit presented was derived from a schematic drawing of our cooling system design. This circuit serves a crucial purpose in our design process, providing a systematic framework for the performing necessary calculations related to the properties and performance of our heatsink. By utilizing this thermal circuit as a guide, we can streamline the calculation process and ensure that our heatsink design meets the required thermal specifications for efficient heat dissipation within the liquid-cooled system. Now, a schematic of a cooling system. This drawing presented here serves as a valuable aid in navigating the design process and realizing our desired objectives. This was created as a visual aid and facilitates communication and collaboration among team members, providing clarity and direction throughout the design process. By using this drawing as a reference point, we can effectively coordinate our efforts, identify potential challenges, and work towards achieving our design goals with precision and efficiency. The final slide. This is a detailed view of our heatsink design. It was meticulously crafted using SolidWorks software, ensuring precision and accuracy in the representation of key components. In this exploited view that's depicted, you can observe the following components, each playing a critical role in the functionality and performance of our liquid-cooled system. Motherboard, the GPU with fins, the housing, the thermal paste. By leveraging SolidWorks software, we were able to visualize and analyze the intricate details of our heatsink design, facilitating comprehensive assessment to meet our design objectives effectively.